let's practice calculating some probabilities. In part A, we want to suppose that we flip a coin 3 times. What is the probability of getting exactly 2 heads? So in these types of problems, I mentioned this in the last video, it really helps to have an understanding of what your sample space looks like. And luckily for us, that's something that we calculated in the last video. So I'm actually going to scroll up here and grab that sample space. We're just going to go ahead and copy and paste it so that we can work with that. It's going to make our lives much, much easier. So we have this sample space. If I want to calculate the probability, and I'm going to write this out the way that I might write it out on a problem, I might say the probability of getting, let's say, get exactly 2 heads. Oops. Heads. So that P just represents the probability. This has the probability of, and then inside the parentheses, I'm going to write my event, in this case, get exactly 2 heads. So I need to know 2 things here. If I'm going to write out my probability, I'm going to say, okay, I'm going to, first of all, need to know how many total outcomes are there within this experiment. And luckily for us, we have the sample space here right in front of us. We can just simply count those. 1, 2, 3, 4, 5, 6, 7, 8. There are a total of 8 outcomes here, so my denominator is going to be 8. And then the next thing I want to do is I want to count the ways that I can get exactly 2 heads. How can I end up with 2 heads in this experiment? Heads, heads, heads. Well, that was 3 heads. Heads, heads, tails. Yep, that has exactly 2 heads. Here, tails, heads, heads has exactly 2 heads, and heads, tails, heads. This grouping down here has exactly 1 head, so that's not going to be a part of my numerator. And then, of course, tails, tails, tails has 0 heads. That's different than 2 heads. So I have 1, 2, 3 total outcomes that I have here. My numerator is going to look like 3. So depending on the problem, some problems might ask you to leave it as a fraction. Some might ask you to give it as a decimal. In this case, if we wanted to leave it as a fraction, we might say 3 out of 8. If we wanted to go ahead and get a decimal of that, that would be 0.375. Some problems may ask you for percentages, but I always prefer the decimal form. It's just a lot easier to use for most of what we're going to do. So either the decimal form or the fraction form, just depending on what the problem is asking for. We'll go ahead and give them both here. Next example, part B, it says, suppose we roll a single fair 6-sided die. What is the probability of getting a 5? Now, in this case, we don't have the sample space, but this is a relatively simple experiment. We can just go ahead and list that out. So the sample space for this experiment, if we roll a single fair 6-sided die, well, you could get 1 through 6. So that would be 1 or 2 or 3 or 4 or 5 or 6. So if I wanted to talk about the probability of getting a 5, let's write that out first. Probability that I get a 5. First of all, I'm going to want to know how many total outcomes are there. Well, there are 6. There's 1 through 6. So there's 6 outcomes for this particular experiment. And then if I look at my numerator, how many of them resulted in a 5? Well, there's only 1. It's the result where I ended up with a 5. So there is 1 outcome where I end up with a 5 out of a total of 6. So our fraction would look like 1 over 6. If we wanted to give a decimal approximation, we would say 0.1667. Let's go and round that to 4 decimal places just to be safe. Again, either one of these is fine. It's just going to depend on what the problem's asking for. Some will ask for a simplified fraction, and some will ask for the decimal form. So that was a relatively simple experiment. We were able to just list the sample space very quickly and count the outcomes that met the event. In this last example, it says, suppose we roll 2 fair 6-sided die and add the total of the faces. What is the probability of getting a 5? This one's a little bit trickier because we have the 2 die rolls instead of the 1, but luckily for us, again, this is something that we talked about in our last examples. So I'm going to go scroll back up. I'm going to grab that sample space. Now, what's kind of tricky here is that we gave this as the sample space for this experiment, but that's not actually what I'm interested in, because if I look at this, the numbers that I have highlighted here, 2, 3, 4, 5, 6, 7, 8, 9, not every one of those outcomes is equally likely. I need to work with something that is equally likely. So what I mean by that is if I look at my table above, there was only one way that I ended up with a 2 versus if I wanted to talk about the outcomes where I ended up with like a 7, there are 1, 2, 3, 4, 5, 6 of those. So not every outcome is equally likely here, which means I would rather look at the table than work with that sample space. So I'm going to go ahead and just copy that sample space. Let me erase my highlighting here just so that we're starting with a clean slate. All right, and let's copy and paste this table. Again, just so that we have it in front of us, it's going to make this problem much, much easier. All right, so we have something that looks like this. I want to know the probability that I get a 5. So again, I need to start by thinking about what's the total number of outcomes within this experiment. That's going to be my denominator. And if you want to, you can go ahead and count them up, or you could say, well, I have 6 outcomes here by 6 outcomes right here. 6 times 6 should give me 36. Or if you'd rather count them up, 1, 2, 3, 4, 5, 6, and so on and so forth, you could, but we are going to end up with 36 total outcomes. You can pause the video to count those up if you don't believe me, but we are going to end up with 36. So then from those 36 outcomes, I want to know how many of them resulted in a 5. So in this case, we're looking at 1, 2, 3, 4 different outcomes. So I have 4 different outcomes that ended up in a 5 out of a total of 36. If I wanted to simplify this fraction, of course I could. These are both divisible by 4, so I'll divide both my numerator and my denominator by 4. Should leave me with 1 over 9. And then if I want the decimal version of that, let me just double check. It should be 0.1 repeating. Yes. So we'll say 0.1111. Again, just depending on what the problem is asking for. So the formula that we use for theoretical probability that we've been using, I want to point out again, is only for equally likely scenarios. I could do that because everything within this table is equally likely to occur versus that sample space that we worked out in our last video. Not every scenario was equally likely because we only had that one scenario that ended up with a 2 where we ended up with actually a whole bunch that ended up with a 7. So as you're calculating these probabilities, make sure you're considering that each outcome is equally likely.